this awesome rebel scum type thing. And I am going to be rebel scum slightly. I'm not exactly going to say, oh, don't use locks. Don't synchronize your code. That way lies madness and excessive need for coffee. But I do want to get you thinking a little bit more, as I call it, outside the synchronization quadrant. And I will explain what I mean by synchronization quadrant. And obviously there is a quadrant diagram involved, which is why they scheduled this at 2 o'clock after lunch, because quadrant diagrams are probably a good match for your intellectual capacity and what your metabolism is trying to do at this point, which is go to sleep. There are many talks at this conference on threading, concurrency, and all kinds of stuff. Where appropriate, I will just delegate to those for the detail. Because it turns out I have too many slides. Okay, so what are we going to do? I've seen that. You might have seen it as well. Thing I edited a few years ago. Things I wrote. This is relevant. It's got the word architecture in the title, which obviously qualifies me automatically to talk about software architecture. So let us talk about software architecture very briefly. Grady Booch had this wonderful definition. And there are many definitions of architecture around. There is no definition that is necessarily correct or incorrect. These definitions are more or less useful than one another because nobody agrees on one definition. You need to find one that tells you something about your software structure. And this is rather interesting. Architecture represents the significant design decisions that shape a system, where significant is measured by cost of change. Now, against all the other definitions you can have, typically the PowerPoint style architecture, okay? These kinds of things, they're all about, architecture is the big boxes. Well, things like concurrency never turn up as being a big box. There's never a big box marked threading. There's never a big box marked distribution, okay? These boxes don't tend to exist as visible artifacts in the way that people draw up their software. Yet they turn out to be not insignificant, okay? So this is the key point. If we start don't get distracted by the packages, the assemblies, the layers, the middleware, and all the rest of it. What you're really interested in is the method of composition, okay? Not merely the artifacts, but the things that glue the artifacts together. And those are more invisible, and sometimes for that invisibility, they surprise us. And these days, everybody's just, okay, concurrency, we're going to do it. Okay, everybody says, we're going to do concurrency. Because why? Because everybody else is doing concurrency. Okay. So there's Me Too syndrome, which is surprisingly popular. Pick a thing you've heard of. There's bound to be a Me Too as well. Okay. Why are we doing microservices? If you went to Russ's talk this morning, why are we doing? Well, they're doing it. Okay. Why are we doing Agile? Well, they're doing it. What do you want from it? Oh, I don't know, something. Now, some people are actually a little bit sharper. Why are you doing concurrency? We want to improve performance. Okay, that's an objective. That's measurable. We can do something with that. But still, we have to build it. And this is the funny thing, and this is a thing I did a few years ago. I still love to refer to it. I did a sort of a word association game. And I did this at 2 different companies, 2 different workshops. Word association game. Up, down, red, black, skyfall, done. Okay, it's the first thing that comes into your head. And I said to this room, one of whom was a room full of people who really wanted a more advanced view of concurrency. So they already knew to get away from the basics. But when you catch people off guard, you say concurrency, threads. It's there, it's just sitting there. But even more revealing is when you say threads, locks, or synchronization. This is what I got from people. It's there. And what's great is you say, okay, so remind me again. You had a clear objective for doing concurrency. Yes, performance. I give you the anti-thread, okay? The whole point of a lock is to eliminate concurrency. That is what it is. It's not there for safety. It is there for the elimination of concurrency. And from that, you may build safety. It turns out you can also build surprisingly unsafe systems with locks. In other words, locks does not equal safety. They are just a tool, okay? You can hit your thumb and indeed the rest of your fingers with the hammer of a lock, okay? Locks do not grace your code with some goodness of safety. They just eliminate concurrency, okay? So, and with that slightly useless power, you can do almost anything. When talking about building architecture, Philip Johnson said, architecture is the art of how to waste space. This is actually surprisingly applicable to a lot of software architecture. So feel free to use that. But given that this is a talk where we're talking about time and concurrency, then I'm going to say architecture is the art of how to waste time. And we do an awful lot of that, particularly in the development process, but also at runtime, without realizing that these are the consequences. So let's have a look at this quadrant diagram, okay? Now, quadrant diagrams, there are lots of different ways of looking at things like concurrency. It generally helps to have only two axes, otherwise they go beyond quadrant and they get difficult to visualize. But in this particular case, it's quite a simple way of looking at things. What we've got here, let's deal with state. Because it turns out that the thread of activity is not the problem. It's the interaction with state. That is the problem. You can have perfectly threaded code that does nothing. Lots of threads, and it's just like perfectly safe. The issue is not the threading. People think in terms of thread safety. It's state safety with respect to threads. That's really, but that's quite a mouthful, so we don't say that. So what kinds of state do we have in our code? Well, we have state that can be changed. It can be mutable, and it can be immutable. It may be permanently immutable. That may be an intrinsic property of the object model. Or it may just be immutable over a period of time. We had an initialization phase where everything was being set up, and then we said, go. From this point on, the data is effectively immutable. It may be by convention. It may be enforced by a type system, by the method interface, whatever. But we have these two concepts. And just a little bit mutable, you know what? That's still mutable, okay? You know, it's the whole little bit pregnant thing. You know, actually, I'm afraid we're going to have to go with the binary one on this one. Okay, and then we have another axis, that of state and its relationship at a given point in time to, say, threads, a unit of activity, the degree of concurrency, okay? Now, I have kind of left off another aspect here because we might occasionally observe that there is code that is actually only safe in the presence of 0 threads. That is a separate talk. I think I did my testing talk 2 years ago. That's what that talk is about. And then there is code where we are dealing with a state being owned by one thread at a time. It may be exclusively and permanently owned by one, or that ownership may change. But regardless of whether or not it changes, so that's just to clarify what I mean by unshared. There are lots of different concepts of what we mean by unshared. I mean, at a given point in time, is it shared across threads? Unshared, shared. Okay, so that gives us 4 quadrants. And just for the purposes of clarification, that's the bad one, the red one. I even chose red and green shades that are comfortable for people who are red-green colorblind, which I am, and I can say I have no problem with this, but if you're still struggling and you're viewing this in black and white, the synchronization quadrant, that is where I'm not saying you don't need synchronization in these other cases. There may be synchronization going on. It may be at a very, very low level, or it may be in a library. The point is whether or not your application code is, you have to sit there and go, we need to lock this. That's the question I'm answering. It turns out that in many cases, it's also equivalent to actually not really having many locks kicking around anyway, and there is an obvious performance benefit. But over here, state is mutable, but we're not sharing anything. So you can change what you like in the privacy of your own code. That's fine. Nobody else can see it. That state change is not visible, so that's not a problem. Over here, we cannot change state. It is immutable. Therefore, I can share that freely across threads because the safety that people desire is, well, you get it for free. It's about state change. And that's the problem. People often fail to identify that that's the real reason that they want to try and lock things. But up here, if you're going to share state and you're going to change it, then you're going to experience pain. And okay, so that's 1/4 of the diagram. Where does most code live? It's like a black hole in the top right-hand corner. It draws all of the code matter in towards it. Okay? There is an accretion disk that we call legacy, just spinning in orbit around it, releasing gamma rays from the developers who fall in. Okay? How did we end up here? When you draw it like this, it's blindingly obvious that, I'm not saying you never ever want to end up there. You may find there are pragmatic reasons to do so, but that should not be your default position. Well, we're going to fall into the black hole, we might as well just jump instead. Yeah, you know, dive in head first. No, resist. See, resist. Rebellion, that's what it's all about, okay? Resist that, okay? Actually, I should be using Death Star metaphors at this point, shouldn't I? Sorry. So we need to look at what goes on around here. Now, so what is this issue that we have? It depends on age group and culture here. Does anybody remember this? 1984, BBC. So it was a program called Threads. It was a made-for-TV film about a nuclear airdrop over Sheffield. The previous year, there was a soap opera of what would happen in nuclear war. It was an American production. It was called The Day After, and it made nuclear war look actually quite palatable, which may explain the current incumbent, the White House. This one was shocking. It was absolutely devastating. We all went into school the next day. I was in sixth form. It's just like pure silence. It's like, that's what it'd be like? Oh, that's the good version. That's Threads. That is apocalypse in your code if you get it wrong. But it turns out, my favorite article title from last year, Immutability Changes Everything, by Pat Helland. It was in Communications of the ACM. That idea of localized immutability or effective immutability, if I change something and I give you copies of it, you know what, you can do what you want with those. As far as I'm concerned, the universe is immutable. It's that shift in perspective. Now, how did we end up in this kind of nuclear holocaust? Well, I did wonder about this a few years ago when I first drew this up. And there's a historical aspect here, and eventually I realized that it's because in the days before threading becoming popular, there was no right-hand side. We were all over on the left-hand side because you couldn't share between threads because there weren't threads. Yeah? It's kind of easy. Now, the thing is that code had gone through a fairly straightforward kind of von Neumann heritage, and for various resource constraints, we end up with very strongly imperative programming languages. Very practical historical perspective. So we naturally gravitated towards this. There are a bunch of people going on about immutable programming, but nobody paid any attention to them because they kept talking about mathematics and stuff like that. So everybody gravitated towards this. So when people added threads, there was a natural migration to this. So if immutability changes everything, then we need to take care of the qualities in our code and be very, very clear. Or rather, if threading changes everything and immutability changes it the other way, what is it that we want from our code? So there's a very simple kind of right-hand rule approach that I've used in a number of ways, a number of times, to try and reason about the changes or properties of a piece of code. And it's not perfect. The angles are not, the axes are not perfectly orthogonal, but then again, neither are my fingers, so I'm good with that. But it turns out to be a reasonably useful model for understanding things like refactoring, optimization, and so on. And if we focus on functional behavior, operational behavior, and developmental aspects, functional behavior is the semantics of the code. This is the stuff you can unit test. This is what it's supposed to do. This is its values. This is its interactions, all of that. The operational aspect is where we normally talk about things like performance, resource usage, stuff that, it's not that we can't measure it, but sometimes to talk about it reasonably is a little bit harder. It's not really about trues and falses. It's much more sort of various shades. It's things like availability and performance and scalability. These don't quite break down with the simplicity of this one. I've got something, it's correct in terms of the results that I get, but it takes too long. It's correct, but it seems to use too much heap. So there's these aspects here. Now, people have a nasty habit, what can only be described as a failure of imagination, of sort of saying, oh, there's functional and there's non-functional. Yeah. So, you know, you could go to a non-ACCU conference. I mean, you know, obviously, whilst we're in the center of the ACCU universe, then there is nothing else. But if you discuss with your colleagues that maybe later in the year you're planning to attend another conference, oh, what is that conference? Oh, it's a non-ACCU conference. Oh, well, that's okay then. we've had the conversation. But that doesn't tell you what it is. It tells you what it isn't. And it turns out that when you start talking about what things are rather than what things aren't, the closer you look, the more there is. And there's something else here. This is about runtime. This is about runtime. This is about development time. The developmental axis, and the reason it's at the bottom is because people normally ignore it. You can't see it. It's got it's invisible. It gets forgotten. The developmental axis is, let's talk about the maintainability, the habitability of the code. What's it like to actually work on that code? I don't care how fast it runs at runtime. Yes, we lost many souls delivering this this particular drop, but hey, good, it runs okay. It's a case of like, no, what was it like to work on that? Is it cost effective? All of these things. So let's just focus for a moment on operational, because people are always going on about, yeah, I want threads to make things fast. Well, obviously, Shakespeare noted this. Shakespeare is one of the greatest programmers ever to have lived, and he had a birthday on Sunday. Sadly, was not here to receive the cake or anything like that. Death, I will talk about object lifetimes at some point later, but this is the monstrosity in love, lady, that the will is infinite and the execution confined. This is the problem. You can imagine all kinds of things. And it turns out that the infinite resources are not available to us, but sometimes we program as if they were. The desire is boundless, but the act is a slave to limits. So we're going to hit a couple of limits a little bit later. So therefore, we have to respect these things. Now, the problem is when people assume we're going to make this multi-threaded, we're going to throw threads at this, we're going to speed things up, as if it's like you just put stripes down the side of your car and it makes it go faster, okay? That was also around at the same time as the Threads film I mentioned earlier on. That was very popular in the early and mid-80s. It turns out it has no aerodynamic effect whatsoever. Okay, so this is a really, really nice logarithmic scale that the IT here put up, I don't know, last year, year before. And it was great because this is how far light will travel in this period of time during the operation. So this is the CPU cycles, and this is how far light will travel in one cycle. And for many years, I have used this as a metric. That is 1 light nanosecond across my laptop, which basically gives you a cycle time of 1 gigahertz, which doesn't sound particularly fast. It turns out that the speed of light is one of those things that you don't get to change. Okay, there is no config file that you go, whoop, speed of light's a bit slow. If we speeded this up, then network behavior would be as fast as in-process behavior. Sorted, okay, ship it. It doesn't work like that. I'm sorry, and this also frustrates many software architects who have that kind of godlike complex, okay? But it's sort of it's quite humbling here, simple register operation. Oh, that's really quick. Memory writes, yeah, this is pretty good. Branching, doing the right branch because pipeline prediction and all the rest of it. The right branch of an if, quite cheap, but if you do the wrong branch, it's a little more expensive. The wrong branch, that's an order of magnitude or so slower. And there's all kinds of wonderful stuff here. All the operations you're expecting to be fast, all the good stuff, L1, L2, L3. This is great. Where the hell's all the thread stuff? Ooh, it's down here. It costs as much as a kernel call. Sometimes people assume that this stuff is for free. It costs something. Throwing a C++ exception. I love it when people say, oh, we're not using exceptions because of performance, but hell, we got threads. You might want to revisit that one. Okay? But what's the real context switch cost? Thread context switch, total cost, including cache and validation. Oh, there's more. You keep spending. Using threads is just like an IT project. Okay, it's always more expensive, and you just keep on spending. And this is the one that costs a lot. Now, I'm not saying don't do this. Clearly, there are reasons to do this. But what you need to understand is there is an initial offset. If you want to use it effectively, then you better be getting some good bang for your buck. The problem you are solving better look right and better benefit from this, because you are potentially introducing some complexities and, importantly, inefficiencies. Now, I always like this way of thinking about multi-threading. So those are the two you need to care about. I always like this way of thinking about multi-threading from the Clue Tray Manifesto, which is a manifesto about business, online business from the late 90s. But I love this way of thinking about the costs of threading, particularly if you're thinking single core, but it's to do with attention span. And David Weinberger, in one sort of box out, mentions multitasking is really just rapid attention switching. That is what a surprising, up until the multi-core era, most threading did not give you any intrinsically better performance. It might give you a certain form of decoupling, it might simplify the composition of certain code, but it did not necessarily give you any better performance, and in fact it could take it away. And because what you are doing, and indeed a ridiculous amount of the history of software or computer science has been devoted to saying we have a single core, how do we make it like, I don't know, a virtual multiprocessor? How do we make it behave like lots? Okay, and it turns out rapid attention switching was the technique. And that's a useful skill, except it takes us a second or two to engage in a new situation we've braced with our focus. It turns out that human beings have this as well, but we really are quite single core. I'll get back to human beings a bit later. They're quite interesting, I hear. So the sum total of attention is actually decreased as we multitask, and then the beautiful metaphor. Slicing your attention, in other words, is less like slicing potatoes than like slicing plums. You always lose some juice. Okay, and you always need to mop up afterwards. I think we can take this one, okay? So, to fully appreciate this type of stuff, let's just imagine that we've got completion time, a task. That's a single thread. And then division of labor, the classic division of labor. N threads. Brilliant. That's where most people stop. It's like, that's great, it's going to speed up. You know, we're going to do that. It's just like, yeah, but look at all the white space. Look at all the white space. You know I'm not going to stop there. How much is your task perfectly parallel? Okay? And this is kind of an interesting thing. So as long as there's the nature of the task, and it turns out, for example, all the people in the room, you're all happily breathing, I hope. You're all happily breathing independently, concurrently with one another, truly in parallel, lots of breathing going on. There is no cost of coordination between any of you until the oxygen runs out, but it's okay, we've left the door open. Until, there's no coordination cost. You can actually do this perfectly in parallel. The problem is that many tasks, by their nature, you're trying to divide up something, and there can be interactions. And you may not be able to squeeze out more than a particular portion in parallel. There is a part of your code that cannot be made faster or cannot be put into a parallel arrangement. And this is Amdahl's law. This is not new. And then some people get as far as this, and they're feeling really good. And they think we're good with that. But we haven't talked about the actual coordination costs. And people know an awful lot about coordination costs in the real world, but sometimes they forget them when they go into the code. Example of coordination costs in the real world, meetings. Okay, so next time you are thinking of stuff like this, when you're thinking about communication in your code, think meetings, okay? And then when you want to put a bottleneck in, use David Butenhoff's phraseology. He wrote the book on POSIX threads. His observation is, we made a mistake in p-threads, calling them mutexes, using Dijkstra's terminology. We should have called them bottlenecks, because then programmers would actively have to stand up there and go, we need to put a bottleneck in here, okay? And they would probably cause themselves to think twice, maybe. But now if I throw meetings at you as well, good grief, this is sounding, okay, we really need to be quite careful about this. And in the worst particular case, all the threads need to talk to all of them, all the other threads. That's the worst possible case. I'm going to explore the worst thread scenario, and there is some communication overhead. Sometimes that communication overhead is associated with a terrible sound. You really need to do something better for your phone. But this is your worst case. But that's what legacy code is. That's why we call it legacy. It is the worst case. It is where everything seems to end up talking to everything else. And as you try and speed one thing up, in order to try and get it going faster, it has to talk to something else. And where's that piece of data coming from? And we need to change this. Oh, but that might be changing it. So put a lock in, put a lock in, put a lock in. So you end up with a curve like that. And so people are, it turns out they're adding loads and loads of cores. And what's interesting is that you actually get a slowdown initially, which surprises people. I've taken a single-threaded app, and I'm on a 2-core machine. I've added 2 threads, and it's now slower than it was with 1. In many cases, that is a cost of coordination in some way. It is either to do with direct locking or other communication overheads, context switching, all of these things. It's a big basket of cost. So be very, very aware. And how do we change these numbers? You change them by changing your architecture. You change them by changing your significant decisions. In other words, how we should approach this stuff. Now, my favorite one when it comes to scaling is this brilliant piece from, it was a blog from 3 years ago, Adam Drake. Command line tools can be 235 times faster than your Hadoop cluster. Everybody got into the habit of saying, oh, big data, we're going to distribute it across the network, we're going to farm out tasks, and it's all gloriously parallel. Remember that thing about the speed of light? Yeah, it turns out that's not the thing you can change. It turns out memory is dirt cheap. If you can co-locate something, always do. Always do. You really cannot beat the speed of light. You may think you're pretty good, but you really cannot beat it. And it turns out that running, as opposed to running an optimized JVM, you can just run some bash tools, and it's actually faster. If you can stick it all in memory, that is your default option. Don't spend time getting faster network cabling. Spend time doubling or quadrupling the amount of memory you have available. Because it's there, it's local, it's cheap. Now, if we're going to talk about Hadoop, that's MapReduce. And I just thought, okay, what does that look like from a general point of view? So throwing in sort of simple C++, we've got the idea of an iterator, range. Here's the operation we're going to map. So you're going to map an operation. That's the bit that's obviously parallel. Then you're going to bring all the results together, and you're going to seed it perhaps with an initial value. You can get the answer. Given that we already know the answer is 42, it seems pointless to run this, but imagine that we're going to do this. Now, of course, I'm going to mix a few languages today, but this is a very C++ biased conference, so you know it doesn't look like that. It looks more like that. And there's stuff in there, and there's dots everywhere, and we're pushing this, and we're doing that, and we're doing this, and oh, God, okay, well, fortunately, some of these things are being solved as time has gone by. This is very kind of C++ 11, and oh, good, we can put auto in. Actually, no, better, we can put auto in. So, this is what we can now do. C++ 17, thank you very much. So basically, you never need to declare anything meaningful about a variable again. What I love about this is there is a beautiful symmetry in time. One of the first programming languages to really show us how to think and reason was Lisp. And one of the fundamental concepts in Lisp is car. And here we have auto. I think there's a sort of a beautiful completeness to that. I'm looking forward to the language that introduces voiture and other things like that as well, so we can get the full family. So there's a few other things we can do. So we're kind of doing a mapping here, and then we're bringing everything together and accumulating stuff. So there's some other opportunities here that are afforded us, and this is the bit that can obviously be parallelized. The new C++ 17, we can now put things into true parallelism, although there's 2 qualifiers. There's par and there's par unsequential. This is the real parallel. The other one is just like, you might do it, it's vaguely concurrent, but this is the one that actually gets the juice out of the processor. So there's a parallel for each, basically, a par for. So we've still got a bottleneck here, potentially. Well, there's not a lot you can do, but it turns out that we can tidy a few things up and get a reduce, which so accumulate, if you've ever wondered, and you're just an STL user, accumulate is reduce misspelt, and always has been. Reduce is easier because for some people they can never remember, do I double the M, do I double the C? It's fine, reduce is much easier, it's much easier to spell. So we have that. So we can really kind of condense things down. Now, this all leads to another point, which is the idea of the composition and simplicity should, in theory, allow us to express functionality. And that's great, but I'm interested here not so much in how we express functionality, that's a different talk, but how do we get it right? It turns out that this is the surprisingly difficult bit, the getting the functionality right. So games programming demigod, John Cormack, wrote this rather good piece on functional programming in C++ a few years back. Henney observed, a large fraction of the flaws in software development are due to programmers not fully understanding all the possible states their code may execute in. And that's a really key idea. What you're trying to do when you write code is you are probably running a version of the code in your head. You are simulating it. The VM of your mind is going through and going, this is going to be like this. This is the state this is in. This is the state this is in, okay? The more complex we make that, the more it defeats our own abilities to reason about our code. So in other words, this is programming for humans. It turns out that we have limitations. We have bandwidth limitations. And it doesn't matter whether or not something is correct, unless you're never going to change it. It's the ability to go back to it and continue to reason about it as hardware and requirements change. It's the basic correctness that I'm interested in here. As Cormack observes, in a multi-threaded environment, the lack of understanding and the resulting problems are greatly amplified, almost to the point of panic if you are paying attention. A lot of programmers don't pay attention and they don't panic. They have that kind of beautiful serenity that like everything is good. And you don't kind of want to disturb them and go, no, 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 no. You know that nuclear holocaust thing I showed you? That's what's happening. You know, there are problems here. So this is where people then sort of say, oh, it's easy. And, you know, right, one of the better quotes, Lambda Calrissian, take me down to Concurrency City where green pretty is, grass the girls, the and are. That's the challenge, okay? But that's only the challenge when we start. This is the race condition issue. But there's more to this. We can lock everything. Oh, but locking, you see, that's the problem. So there's a nice piece studying the problems of deadlock, as described in Tannenbaum's operating system book. There are several ways to address the problem of deadlock. Just ignore it and hope it doesn't happen. It actually has a name. It's called the ostrich algorithm. Okay? Yeah, you know, apparently this is actually quite successful. As well as being quite popular, it is surprisingly successful. The problem, though, is, and this is one of those issues that we're getting from scaling, is that people are now running things more. And it turns out that, I'm not saying, you know, you still get the once in a blue moon concurrency bugs, but it turns out that these things become harder to tolerate now that we are running so many more instances so much faster. These things become more frequent. Detection and recovery. If it happens, take action. Okay. Now that leads people. I mean, there's whole computer science departments devoted to deadlock detection, how to put it into reasonable languages, and so on. And this is not an unreasonable thing to do. But at one level, it seems to be we're putting our energy into solving the wrong problem. Dynamic avoidance by careful resource allocation. Check to see if a resource can be granted, and if granting it will cause a deadlock, don't grant it. Okay, so now we're moving into, let's shift this problem over to be a dynamic one, a program one. Often we offer non-blocking interfaces and things like that. We've got a sort of more dynamic approach. The problem here is that it can push up the functional complexity of the code. The other problem here is that the correctness of the code can still be hard to determine. It doesn't matter how clever you are. The correctness of the code, the problem is that good code looks just as convincing as bad code. Okay, it looks just as correct. And sometimes if you're looking at things and you're doing particularly low lock techniques and you're sitting there going, I think this is okay. And you know, you'll come back 6 months later having woken up in the middle of the night in a cold sweat going, no, it's not okay. I've just remembered something obscure. And you go in and you check, and there it is. And that might have explained the intermittent bug you've been having the last few weeks. The problem here is that it looked convincing. And that becomes the challenge. It becomes difficult for us to work with. Prevention, change the rules. Now, I quite like this one. Let's change the rules. So let's change how we approach the code from a developmental aspect. What do we want from our code? We want it to be reasonably habitable. Habitable is, we're talking about architecture. Architecture defines a space in which you live. Okay, well, let's work that metaphor. Quote from Dick Gabriel, who in his book Patterns of Software made this point. Habitability is the characteristic of source code that enables programmers and people coming to the code later in its life to understand its construction and intentions and to change it comfortably and confidently. Now, I normally talk about this in the context of code, general code quality and things like technical debt. But when we start thinking about this in terms of concurrent code and the use of threading and various other primitives. Yes, you may know how to use a lock. You may know how to use atomics. You may know how to use all of these things. That's great. It's not necessary. I mean, if you don't, then that's not so great. But even if you do, that's you today. There are other people, and in future you will be another person. Okay? You're looking at this situation, and it's that really interesting qualification. Does this objective hold true? Understand its construction and intentions. When you go back or when you go to somebody's code that is oh so clever, do you understand its construction and intentions? Maybe it's at the edge of your understanding. If it's at the edge of your understanding, you're not going to want to change it comfortably. Okay, but there's no confidence there. That's not going to. That's not going to. Your instinct is to be human. You know, fight it or run away. Okay. Well, actually, there's the 4 Fs, and actually, you might do one of the other ones. So there is this challenge. That's what we want. Habitability makes a place livable like home, and this is what we want in software. Developers feel at home, can place their hands on any item without having to think deeply about where it is. Conceptually, they have a good working model in their head. Now, at my home, we have multiple threads. There's me, my wife, and my 2 boys. Okay, and you know, I've got a teenager and a tweenager. Good God, if you want to talk about rogue threads. Okay. But somehow the whole house works. It is comfortable. You know, things are not always where you expect them to be. You know, you put things down, you come back, where did that go? You know, there's all kinds of stuff going on. But I'd say you don't have a lot of locks in the household. Yeah. So the point here is there's not a lot of collisions. There's a notion of there is comfort. You can expect things. So it turns out humans can work with threading, or rather we can work with concurrency. We can understand basic concepts of parallelism as well. But our motivation in many cases from a coding point of view is we want things to be testable. Not just because it demonstrates a certain correctness. And I'm not talking about testing out the concurrency bugs. I'm talking about the other kinds of testability. And in the sense that testability is a useful proxy for many other behaviors. So when we talk about loose coupling, what does that feel like? What does loose coupling feel like? Because people use terms like low coupling, high cohesion, as if they had some intrinsic meaning. But they don't really until you can actually feel them. And testability is a way of trying to feel it. Is this code testable? Well, no, it isn't. It's an absolute nightmare. Okay, so therefore your statement about loosely coupled does not hold up to reality. So it's a stand-in for many other qualities. Now, given that, I mean, there are other reasons. There are correctness reasons, basic functionality aspects. There was a brilliant paper 3 years ago, Yuan and others. Simple testing can prevent most critical failures. I love papers that have such simple titles. It really is exactly what it says on the tin. They analyzed a number of open source systems. One of the most interesting findings was, majority of the production failures, 77%, so we're talking about 3/4, can be reproduced by a unit test. It doesn't mean that you would have necessarily found them, but when you go back, yes, it turns out you can do this. So it turns out these things are surprisingly useful. And it's this idea of unit we need to understand. What is a unit test? Because that's going to tell us something about the qualities that we want, what we want from code that is designed to be used concurrently. And this is a really important aspect because this is code for humans. So people often start off, we want our code to be unit testable. That's great. That's lovely. Why do you want it to be unit testable? Because management said so, because my friend's doing it. There's all of these things. But there may also be other good reasons. We want to be able to refactor freely. We want to be able to go into production with some kind of confidence. We want all kinds of other stuff, we want to be able to do better than belief. Is it going to work? I believe so. Beliefs are lovely things, but occasionally you have to try and convert them into something of substance, a currency called knowledge. I know and I can demonstrate this. What is a unit test? Oh, I had to ask that question. Okay. What is software architecture? What is a unit? These are actually surprisingly difficult questions because not everybody agrees on the answers. But I'm going to go back to what I did with software architecture. We can start saying, well, what is a useful definition? What is one that tells us about the thing that we're building? Now, one of the most common definitions used from Michael Feathers, a set of unit testing rules. He also includes this in his Working Effectively with Legacy codebook. A test is not a unit test if, so he defines it negatively, it talks to the database, communicates across the network, touches the file system, can't run at the same time as any of your other unit tests. That's interesting. Okay, that's an interesting point here. I mean, I'm just going to say, because I don't normally ever talk about singleton, but yeah, singleton. You have to do special things to your environment, such as editing config files to run it. Now, he says these things aren't bad, but he's sort of saying, look, let's understand this. There's a performance thing here, but we can actually go a step further. My definition from a few years ago was a kind of simpler one. I wrote this one on the register 10 years ago. A unit test is a test of behavior whose success or failure is wholly determined by the correctness of the test and the correctness of the unit under test. In other words, if it passes, it's because of that code there. If it fails, it's because of that code there. Okay, very, very simple. You don't have to look anywhere else. Importantly, you don't have to sort of look out to the network, look at the file system. You don't have to look at anything that may have changed, passwords, permissions, or any of this stuff. The it worked on my machine type thing. The point here is that it's down to the correctness of the code, and that gives us a more decent way of looking at it. It's to do with isolation. Isolation is a very useful property. So let's ask a different question. You're entitled to ask questions of your code. In fact, even better, I'm going to phrase these as requirements. You're allowed to have requirements on your code. You're allowed to have requirements about your development practices. People often think requirements are things that come from customers or managers or whatever. But when you adopt a tool or a practice, there's the question of what would you like to have from it? What do you want from this practice? That normally flummoxes most people. Well, what do you mean, what do we want from it? Well, you're about to adopt a naming convention. What did you want from your naming convention? You're about to add threads into your code. What do you want from it? You can be very, very precise. What do you want from your unit tests? And this is a surprisingly simple question which people are often unable to answer. Why, what do you want from a unit test? Now, the simple answer is also wildly incorrect. A lot of people want, when a unit test passes, it shows the code is correct. Sorry. I can say, when a unit test passes, it gives you kind of warm fuzzies and some sense of confidence, but that's not the same. So but don't underestimate. Confidence is very useful. No, what I want is when a unit test fails, it shows the code is incorrect. That is a different thing, and we find that surprisingly many tests do not satisfy this. They fail for reasons that are, what happened? Why did that test fail? Because we changed the code. Okay, was the code wrong? No, it was better. So wait a minute, our tests fail because we've improved the results of the code. Okay, they're not very good tests, are they? Okay, in other words, you've over-asserted. You've asserted on something that is far too precise. That is not really part of the requirement. It's an artifact of the implementation. Alternatively, this failed. What was wrong with our code? Absolutely nothing. It turns out the universe was broken. Okay? In other words, the world around the code, the file system, the network, and all the rest of it. So this is a surprisingly, I'd just say, this is a really simple way of looking at what a unit test should be, and a good unit test. And you may find this actually surprisingly difficult to achieve as a goal. But given that, it starts telling us about the composition, what we want from our code, from any form. I'm not going to give up the rules. Oh, we're doing multi-threaded code, so therefore none of this matters. Absolutely not. It matters even more. We get the problems are amplified. So I need to understand isolation is a valuable property. Immutability is a valuable property. So what are the things that make life easy for human beings? If something doesn't change, then that's really easy to reason about. Okay, so I was helping my teenager with his maths last night, and there were equations involved, but there was something I didn't know from the point of view of the teaching syllabus. But I said I can deduce that this is probably what is going on. Oh, that's not the way we were taught in class. I said, yeah, but I think you might have misunderstood what you were talking about in class, because the one thing I can guarantee is that number 2 is still 2. Because if we do it your way, this is no longer an equation where things are supposed to be equal. I said it less aggressively. I said it properly dad style, okay? But, I'm saying the point here is that there are things that I can guarantee. When you went to school this morning, they did not switch the value of 2 around, okay? There are basic things about the equality of this expression that must hold, and I'm comfortable with that. It makes my reasoning easier. There's another thing that makes reasoning easier: sequential. Here we find the bind. Here we find the bind, because it turns out we're actually quite good at this. Although, as I said earlier on, there is code that is not even good enough to be sequential code, but there is this idea. We are quite good. This happens, then that happens, and then that happens. And it turns out that that is one of the attractions of the obvious point about imperative programming languages. It's not the state change, it's the sequence. Do this, do that, do the other. That's very appealing. It turns out there are other models that are easy to reason about in sequence, and we'll hit those. But the idea is that that is the attraction. It's the state, it's the state bit that doesn't achieve that, that's nasty. Mutable in sequential is a pain in the backside. But I want immutable in sequential. But there's not a lot of space here for what we might call programming. Okay? It sort of narrows down a little bit. So we kind of loosen things up. Well, how do I have lots of things in sequence without any kind of interference? If I want to get things done, I can have them executing without interference. Well, that's great, and they're each sequential. But occasionally, we need to interact with things. It turns out one of the ways of scaling things easily is asynchrony. Things that are asynchronous. In other words, localized sequences. In some places, things look very, very sequential. In other places, however, there is a consequence to this. Nothing is for free. One of my favorite tweets on this. 10 things you'll find shocking about asynchronous operations. 3, 2, 7, 4, 6, 1, 9, 10, 5, 8. Lovely. Beautiful. It's one of the best tweets I've ever encountered. But it still gives us a starting point for how to reason. What we want from our code is, if we imagine, start with a blank sheet. Instead of thinking about threads executing in a space that is shared, let us think very, very simply in terms of single-threaded bubbles. There is a bubble of code. It has its reality. It has its own local state. It can do what it likes with its own local state. It's effectively a process, okay? But it's not necessarily an operating system process, but this is our model of reasoning. And it turns out life is good inside. And, you know, we can handle things from the outside, messages and events, because I can sit here and I can say, I'm ready to receive. I'm ready to receive. I'm ready to send. I'm ready to receive. It turns out that it's easy to reason about that. Okay? In other words, it goes through its little sequential life. Where do those messages come from? Who knows? Okay? It lives in its own little bubble. Okay? This is, or rather we should say echo chamber these days, but it lives in its own little bubble. It's its own beautiful universe where everything seems to work out really nicely. And it's easy to reason about. It's also surprisingly easy to test. It is isolated. And this is great stuff. This is not how most people approach threading. What they do is they say, right, I've got sequential stuff, or rather, here's what this looks like, here are my objects, and now, okay, ready to fire threads? And we're going to just fire threads across the object model, okay? And, oh, that's going to hit that, so lock that, lock that, lock that. And it becomes a very, very sort of like ad hoc approach to reasoning. But this idea, that's an illusion I want to preserve because it's easy to test and it's easy to reason about. In this case, testability is the proxy for I can think about it easily. I can understand it. And then what we have is these other guys. And that kind of style of thinking, we compose a system out of little pieces of sequential stuff that don't tend to block each other and talk relatively asynchronously, but they do not talk directly to other threads or to shared state. Well, if they talk to other threads, they talk to their queues. It depends on the abstractions we're using. And a few years ago, I mentioned earlier on the virtual multiprocessor model. This is the inverse. This is the virtual uniprocessor model. And in many ways, you're already familiar with that. It's a good model for the stream of consciousness. You believe that things happen in sequence and your brain does, oh, it's great, it's a beautiful illusion that is running on top of the most ridiculously parallel hardware I know of, okay? Your brain is not sequential, okay? But you have an illusion of order and things happen in sequence. Oh, I just had an idea. Actually, that was a low-level routine that just popped something into the queue, okay? And you're now ready and available to listen to that idea. That might be an oversimplification, but actually, I think that's probably better than most human beings manage. But so this idea of virtual uniprocessor, what we're going to do is we're going to take concurrency that is innate and inherent in the underlying platform, and we're going to say, you know what, wherever you are, it should look sequential. We're going to do the exact opposite. How do we support this? Well, a number of different techniques. One of the classic patterns in this space is a future. It's a virtual proxy. I'm going to return you an object that's not really there. It's a promise. It's an IOU. It's a placeholder. I'm going to give you an object, and in future you can come back to it. So I'm not going to give you a value when I compute something. I'm going to give you the promise that you can come back to it. Okay? So that's great, and we get that in C++ 11 onwards. We can sort of transform something like a very simple function call. Maybe this takes a while, and we can say, well, maybe I want to do other things. Maybe I want to do something afterwards or before, but actually there's other, this is costly. What I really want to do is do something at the same time. And again, there's this idea of I don't want to have to care. And this is actually an example of something that is concurrent. It could execute after or before or at the same time as. We don't really care. And the way that we can express this idea, one of the many approaches, is to say we'll have an asynchronous function call. Okay? We will basically say, execute it, I'll come back for the result later. And a very simple model at that. So that, in C++ 11, it kind of looks a bit like this, and we come back and we pick it up later. I preferred a different style when I proposed a number of years ago, which is to make sure that everything was actually looked like a function. So thread is a verb, not a noun. You thread a function, and you can thread it with a pool, you can thread it with something else, and what you get back is not an object with get. You get back an object that is a function object. In other words, it yields a value when it's called. Okay, it's a very simple idea. It's kind of cute, but nonetheless, same kind of effect. Okay, so we're going to need to take this a bit further, because it turns out that although that's really useful for long-running tasks and asynchronous tasks, things like I/O, where we may say, I know I'm going to need that, I need this to be loaded across the network, but I don't need it just yet, but somebody has to do it, in which case async I/O is an absolutely brilliant idea, nice and easy. I have a long-running computation. I have all the values that I need to kick it off, but there's other stuff I want to be doing, like responding to the user. So there's that idea, but not everything can be fitted into that. It turns out most computations need a little bit more. Okay, so let's go and have a look at what Russell said in one of his contributions to 97 Things. Message passing leads to better scalability in parallel systems. That's another one of those great titles. Well, no ambiguity about what his piece is about. And he revisits exactly this idea. Instead of using threads and shared memory as our programming model, we can use processes and message passing. Process here just means a protected, independent state with executing code, not necessarily an OS process. Languages such as Erlang and Occam before it have shown that processes are a very successful mechanism for such things. And such systems do not have the synchronization stresses that shared memory multi-threaded systems have. So a number of points there, synchronization, shared memory, but performance is the emphasis here. I want to come at it from a different point of view. I want to come at it from the point of view of composability and the ability to reason about things. And what you'll find is when you start looking at any of these things, is a lot of stuff is based around queues. So what kinds of queues are there? Well, there are obviously queues to try and get a coffee, and queues to get to the room, queues for lunch. But we can actually come up with a reasonable understanding of the kinds of queues that we want. Here we have a one-to-one queue. Producer, consumer, queue in the middle. We can also have fan-in. We can also have an n-to-one. The idea is that the queue is gathering things. Perhaps these are disparate sources of data. Or alternatively, the rate at which each one of these is produced is lower than the rate that we can consume them. And so we use this as a kind of a stepper in that sense. So that's a valid model of composition. An alternative one is the opposite one. So we sort of, the idea of I'm doing this and this will be scattered to the corners of the earth, or other people are picking up worker threads, are doing something meaningful with them. So that's a different kind of thing. What is interesting about each of these is we often speak of queues as if they're totally generic. We need to be very careful with that, because each one of these can have very different locking strategies. If you understand that something is a one-to-one, it's going to look very different to an optimized version of one of these. And it also encourages you to think in terms of, rather than locking things yourself, is to use other people's abstractions or craft your own abstractions so they look like something familiar and easy to use. Many to many, doesn't have to be the same number. And many queues going to different ones. So you can play this game for hours. And then obviously you can do that. Okay, so if I were to do this in C++, then actually there isn't really one in the library. So we sit around and start making stuff up. What are the basic primitives? So I'll build up a couple of bits and pieces. I don't want this code to be the kind of the core emphasis, but I want to sort of show some of the points that I want to make, and most of these are also true in other languages, but normally with less syntax. One of the simplest ways we can do something is to send and to try and receive, a non-blocking receive. I'm going to send something along a queue, and I'll try and receive. If there's something there, then I get true and a value is changed. If there isn't something there, I get false and the out parameter is not modified. And I'll go ahead and I'll use a deck, given that it's in theory supposed to be good at this. So things we might do. This is nice and simple. Okay, we push something to the back, and then to receive, if it's empty, it's going to be false. Oh, this is all great. It's also painfully single-threaded. But this is where to start from, because actually it turns out you can write tests for this. And in a single-threaded, this is the other thing, is this queue should also work in a single-threaded environment. So actually, it's a reasonable stepping stone. Just don't check it in and give people the impression that, hey, we're done. Otherwise, there's going to be some exciting moments a little bit later on. That's not the kind of excitement you want in software development. But nonetheless, it shows you there is a progressive stepping stone. We start from sequential reasoning. What do we want? How do we want to use it? What would it look like if there were no other threads? Yeah, so I did, many years ago, I did a master's degree in parallel computer systems, and one of the best things I messed about with was getting an application, definitely pre-cloud era, running across all the workstations. It was developed on a PC that was not connected to a network, because if it can't work for n equals 1, it definitely won't work for n is greater than 1. Okay? And it turned out one of the most valuable lessons was to be able to understand that in the limit, this should work as it stands. Okay, so maybe we actually want to make some threading of this. Okay, so that's fine. So we throw that one in, we throw in a lock there, and we throw in a bit, it's getting a little more involved here, but it's still reasonably good. And we've got that. We may also decide to take the next step and actually have a blocking receive, now that we can do that. Okay, so that's a blocking receive. Okay, if we have a blocking receive, then nothing happens until a value comes in. Okay. And because we're feeling good, let's have a try send as well. And also a maximum size. And, this is getting interesting. I'm going to come back to the maximum size later. But it turns out that you may not want to have, you may not want to assume you have infinite memory. Just one of those kind of small suggestions, okay? Therefore, if we do that, if we start imposing limits, then we have the idea that a send can fail as well as a receive. Things can be full. Okay, and it gets kind of more exciting. You now have to put in a whole lot of conditional stuff. I'm going to ignore most of that because it's fun as it is. I'm not going to include it just at the moment. Okay, so send, that does that, and all kinds of good stuff. Conditional variables, again, there are other talks that are dealing with this kind of stuff. So all of this is good and reasonable. Now, how do we come to actually start trying to use it? Well, people like syntax sugar. It's C++. We might as well use it for something. Syntax sugaring. Streaming operators. I could easily add in iterators here. What we're doing here is we're recognizing that if you're going to offer people a programming model, offer them something that feels comfortable and familiar. Sometimes people want to work with iterators, and an iterator way of viewing a series of values coming from somewhere else is entirely reasonable. Alternatively, stream operators, that's a reasonable personality. Alternatively, function calls. In other words, I want to say I'm calling a function and it produces something, and so therefore I want a function object approach. There are all of these. Don't do them all at once, though. Otherwise, that's one of those wretched APIs that try to keep all the people happy all of the time. Do not do this. They will be miserable for most of the time. So there is this idea of you've got a number of choices here. And we can do a few other things, and there's other bits and pieces. I'm going to skip all that. I'll leave that in the slides. So all this is good. Let's go back to that point I made. There's a queue. The thing that matters here, it has a size, n. It's maximum capacity. It buffers. It's bounded to an upper size. That means it's asynchronous up to a point. It will block at some point. It may, you have to account for that possibility. That turns out to be quite difficult. buffered, unbounded, asynchronous. That's perfectly asynchronous. The problem is if you have any rogue code, any code that is blocking anything, you can fill up all of memory. And you can, oh, but I got lots of memory. Trust me, it will find it. Okay? If you have something that's not quite working, all it takes is something 1 bit not quite working at multiple gigahertz, and it turns out that, yeah, suddenly goodbye memory and goodbye functioning system. So having the idea, so it's great for prototyping and messing about, and it's really good in textbooks, but you really do want to have an n in there. Now there's some interesting things. If we start messing about with the value of n is 1, single place q. It's buffered, it's bounded, clearly, it's asynchronous up to a point. The limit, that's the limit of asynchrony. We actually have another name for this. It's called a future. Okay? A queue of 1 is a future and a promise. It's a really simple way of looking at it. It turns out there is, whenever people talk about programming, whenever they talk about concurrency primitives, they're never primitive enough. You can actually reduce things to an even lower level. And what does this mean in terms of synchronous programming? Well, synchronous programming is simply n equals 0. Unbuffered, bounded, synchronous. Okay, so we can basically recreate. You can recreate. This is the purpose of process calculus, is to recreate all of computer science using queues. Yeah? Okay. It's a little bit like the projects of the early 20th century to try and unify maths under one heading and so on. It has some interesting consequences. Now, this really kind of kicked off with work on channels. A lot of this stuff we credit Tony Hall, CSP, Communicated Sequential Processes. This was the basis of the Occam language that I mentioned in that quote earlier on. Now, channels have an interesting thing. The terminology is sometimes appropriated to mean different things, but strictly speaking, a channel really is one-to-one. And so therefore, in many cases where people have used the word channel, they actually mean queue, because they've got n to 1 or n to n. And so on. But it really is one-to-one. It's a dedicated channel between, it's old-style phone call. Okay, there's really 2 endpoints. So that idea very, very much fits the idea of a classic future and promise, whereas if you start raising n, you end up with a shared future. So we need to apply this to a real problem, like FizzBuzz. It's okay, we'll look at some other real problems later. So what's that going to look like? Well, the language that people tend to talk about in terms of channels these days is Go. And I'm going to write some utterly pointless code here. What I like is that this particular function demonstrates Go at its weakest. Actually doing things with numbers and making conditions. I mean, it has some really nice aspects, but honestly, it's just like, okay, if you used a proper language like Python, then it would be much shorter. But yeah, it's a case of like, this is really quite, I can do FizzBuzz in a tweet in Python, but not in Go. Okay, so we've got a function that does FizzBuzz. If you're not entirely sure about what FizzBuzz is, one of the great things about this conference is the bar culture. Okay, FizzBuzz is a drinking game, although Wikipedia will try and deceive you into thinking it's a children's game for learning division and multiplication. But actually, I've always known it as a drinking game, and it's a very simple drinking game. In fact, it's utterly pointless in a group of people who are numerate and sober, which is why the alcohol helps. And it is a counting game. 1, 2, fizz. You replace everything divisible by 3 with fizz. 4, buzz. Everything divisible by 5 with buzz. Fizz, 7, 8, 9. Oops, should have been fizz, have a drink. Okay, and that's the game. When you hit 15, divisible by both 3 and 5, you get FizzBuzz. Okay, and there's lots of different ways of solving this. I actually had a whole talk devoted to this. I've actually collected enough versions of it to run a 3-hour talk. I will bore you with that another year, and there are some crazy, crazy versions out there. So, that is the basic thing. Now, obviously, this being software development, that's the function. We need to set up a server. Of course we do. It's a FizzBuzzer, and that's what it's going to do. We've got a channel that comes in and a channel that goes out. We receive ints and we emit strings. And we're going to cover the range of the input, and we're going to pull out a value each time round. And there's actually not a lot of concurrency in this problem at all. But nonetheless, we will push out a value of a converted value. And that all works out reasonably well. And then main just basically sets up 2 channels. We launch in a Go routine, we launch the FizzBuzzer server, and we wire it up, and then we iterate through, and we pick up, convert. Normally the problem is defined over the domain 1 to 100. And we do the conversions. So, you know, it's one of those classic examples of software developers taking an easy problem and actually making it far harder. There is no concurrency in this problem whatsoever. However, sometimes taking things that are really simple and messing about with them reveals some profound insights. Okay. So I just demonstrated before that, you know, made that point that particularly if we think of a channel of with a bounding of 1, a single place channel, then that is equivalent to a future. A channel with 0 buffering is equivalent to basically a synchronous communication. Both parties have to be there simultaneously. It turns out, so this is not Go. I'm going to use a slightly different language here. This is Occam. You can't really find around these days, but it's one of the most interesting languages from a point of view of design. It's a language that is space sensitive in terms of indentation, dictates the block level. It is also the most insanely typed language, or the most strictly typed language I've ever used. If your program compiles, there is a ridiculously high chance it is correct. You know, casts, no. The looseness of these other languages we play with, not at all. It is the, it doesn't even give you compiler errors. It gives you a compiler error, singular. Okay. In other words, if the code doesn't compile, if it encounters a syntax error, type mismatch, or anything like that, it says, right, I'm stopping. That's it. You can't be bothered. Neither can I. That's it. I'm not. There is no message cascade. It's just like you fix it. I'll come back to me when you're done. It's just, you know, if you can program with that, you can program with anything. But one of the most interesting things I remember having kind of a moment of insight about this is an assignment of an expression, the resultant expression to a variable, is equivalent to 2 synchronous channel communications. In other words, zero buffering. Par means the block is to be executed in parallel. It's your open, close, curly, but for parallelism. If you want it sequentially, you type SEQ. It's a really simple concept. So here's our channel. That's a send, and that's a receive. And that is actually equivalent to that, except that it's obviously slower and a complete waste of concurrency, except that it's a profound insight that assignment is actually a send and a receive done in parallel. It's just like, okay. It turns out when you have these little moments, it turns out you can start converting other things in your code. Okay, when you realize that a future, if you realize that you are creating lots of queues that are single place, then use an abstraction that looks like that. It's a future. On the other hand, if you find that you're doing an awful lot of future communication and you kind of wish you could do more, but you're blocking a little bit more than you expected, then maybe that's actually be a fully fledged queue. So we can kind of mess about with that, and I'm not, there's some C++ code there, I'm going to skip that. But it gets a little more interesting when we say, well, what's one of the most common applications of this? Well, pipes and filters. Turns out pipes and filters are the other style of, one of the other styles of sequential reasoning that we are really good at. People often think that sequence means just a sequence in time and it's imperative. But it turns out that sequences of things arranged in a pipe and filter fashion are also quite easy to reason about, but they are intrinsically and inherently concurrent, which is rather useful. So in other words, what I'm going to say, the advice is to, wherever you can, look for sequences. And it doesn't mean semicolon-based sequences. It can mean pipe-based sequences. So what we mean by pipes and filters, divide a task into several self-contained steps and connect these steps to a pipeline via intermediate data buffers. And so now we have a much more clear choice as to what we're trying to do. So the motivation for that is, so we've got an asynchronous function model, we've got a general queuing model, and now we've got a pipeline model. It turns out a surprising amount of processing fits into this stuff. It is also, to satisfy various desires, this is also a functional programming model, particularly it's referred to as concatenative programming. So called because it uses function composition instead of function application. Lisp is an applicative language, for example. An example of a concatenative language is the Unix pipe system. It turns out that is a functional system. There are no visible side effects during a pipeline. There may be side effects within each process, but that is unshared mutable state. But the whole notion there is a pipeline of composition, simple elements with a simple model of composition. Now, what we can end up with is something that looks like this: source, filter, and we can re-express things as filters, and then we can have a sink. So a problem that I've used this in a previous talk, but I'll go back to it. One of my hobbies is taking photographs of books. It's easier than taking photographs of people. A book never looks at the camera funny. Never has its eyes closed or anything like that. But specifically here, I also run a page on Facebook called Word Friday. It started with the idea I present an unusual word every Friday along with its definition. And it's expanded. I put other language and word-related stuff up there every now and then. But one of my favourite words is paraskevidekatriophobia. You can catch me in the bar later to see if I can still say that. Superstitious fear of Friday the 13th. So therefore, for your superstitious friends, we need to find out. Yes?
The Greek people already know the word.
The Greeks know an awful lot of stuff. The problem is they encoded it in an alphabet that very few other people can understand. Which I think is really, I think it's really clever. We're going to put this in plain. We're going to hide the wealth of human knowledge in plain sight, but we're not going to use that ridiculous Roman alphabet those usurpers across the Aegean chose. We're going to use this in a different coding form, and all of human knowledge is there. So you're right, exactly. And it's the rest of us to have to kind of figure it out. Russians have kind of but Russian is a language mostly about suffering. So how do we turn what is obviously a simple algorithmic problem into a pipeline? And this is, again, reassessing the primitives so that you can scale up. We're going to have a source of days. Then we're going to pick out all the days that are the 13th of the month. Then we're going to pick out all the Fridays. And then we're going to do whatever it is that we wanted to with them. So therefore, a pipeline sequence at this level looks like an AND, effectively. So that's kind of interesting. Now, if you use something like PowerShell, let's say we've got some number. Let's look at the next 1,000 days, max. 1 to max, pipe that into add days, whatever the start day is. Let's just say Alien Day, 26th of April, or April 26th. And then add the number of days. Now, that's a simple pipeline there that produces a source of dates correctly typed. Then we're going to filter that based on whether or not the day in the month is 13. Then we're going to filter that based on whether the day of the week is Friday. And then, boom, we've got something. So it fits rather nicely there. It's a sort of it's a profoundly inefficient way to do it. But it turns out that the basic idea here scales. This is why people are so excited about pipeline architectures. It turns out that most of the things you want to do at scale are just big versions of the things you do in the small. When I mentioned Hadoop earlier on, MapReduce, that's just a big version of two fundamental primitives, map an operation and fold all the results together, but now scaled up. So there's this idea that things in the large tend to be scaled up versions of things in the small. So never kind of look at an idea and go, that's ridiculous, why would anybody ever want to do that? Because there's normally some deep, profound truth that will normally come to you, on the way home. So if we do this in C++, more code. And actually, it doesn't make a lot of difference. I tried it if you use the Chrono library. It just saves you one line. That's about it. So we can now create a pipeline. We're going to have the days from the start date, and we're going to have a channel that's going to produce days. And then we're going to loop round, and we're just going to write out the results. We're going to use the stream operator. Here's the next day. Here's the next day. Here's the next day. Here's the next day. And then we're going to go to the next one, and we only want the 13th. OK, we only need to select the 13th. We take an input, we give an output. We go through all of the input, and if the day is 13, then we write it out. Really simple filter model. Same deal with Fridays, and then, boom, we can print them out. So there's a very simple idea of a compositional approach. What is nice here is that the units of composition are all small. They are all side effect free. Okay? They work only on their arguments. They work only on their parameters. And this is a classic example of a sort of parameterizing from above. It's also very easy to compose with. Simple filters that can be arbitrarily chained are more easily reused and more robust than almost any other kind of code, was an observation Brandon Rhodes made a couple of years ago. And there's a very deep truth to this idea of, does my problem look like a data flow problem? Can I rethink it into that? Sometimes you have to torture it a little bit, like the Friday the 13th one. But actually, you'd be surprised how many things look like a pipeline or can be made to look like a pipeline. And the value of that is that each component of that pipeline is easy to read and reason about and easy to test. Each one of those little elements can be tested completely in isolation from the other. It does not need threading. There's no visible locking. Sure, there's locking going on the inside of the channel. It may be relatively low lock, because if it's a proper channel, one consumer, one producer, you can choose a nice low lock strategy for that. But the idea there is that you can actually test this quite freely and test its majority of its correctness in isolation. And that gives you kind of a simple confidence, as I said, confidence, don't underestimate it, to build up more complex things. Here's an example I swiped from a paper that was actually on Go and reasoning about it. And I thought, actually, I'll present the code as is, reorganize it. But it was quite a cute way, it's kind of classic example of using dynamic channels and creating a filtering model. And again, rethinking. What we're going to do here is we're going to generate all the numbers from 2, all the integers from 2. We're just going to keep pumping these out. What we'll then do is figure out, is that divisible by the prime that's been given me? Okay, we're going to read in a value. And if it is divisible, we're not interested in it. If it's not divisible, well, you know what? Let's pass it along to the next person in the chain. That could be quite interesting for them. Not for me, but I found that, well, it's passed my prime test. I passed my prime. Okay, I should have revisited that sentence a little more carefully. I like to think I'm not past my prime, but let's just pass that to the next one and find out if it is a prime. So we're going to set up a pipeline here of little nodes, little filters that filter out primes. But obviously, well, how far does this go? Well, as far as you want, because it turns out you can just set this one up, and it's kind of a little bit like setting out the track. It's in that Wallace and Gromit film, there is the point where Gromit actually lays out the track that his train is going on just as he arrives at classic cartoon territory. But that's exactly what's going on here. We get a prime back, we make a channel, we wire it up to the next one, and we lay the next bit of the track and say, okay, well, it turns out 5 is a prime. We've already figured out 2 and 3. 5 is a prime. Okay, the next read back tells us that, well, 6 didn't get through because it failed on 2. Oh, look, 7 managed to run the gauntlet. Okay, here's a node for 7, and let's run the next number through. And so you have this really quite elegant way, and also it's elegant. It's also, there's a slight infinity problem here, which is why I've sort of said I'm presenting it as is. But nonetheless, if you want to put in real-world stuff, then that changes the font size. But nonetheless, there's an idea here that I think is worth exploring. Okay, so what other ways of reasoning and organizing our code are there? Well, I mentioned a number of years ago I did this thing on parallel computer systems. My thesis was on actor-based computation, this language in particular, ABCL. And I think the simplest way of thinking about actor reasoning or actor models is very much the virtual uniprocessor approach that I described earlier on. Andrei Alexandrescu has a lovely quote, multi-threading is just one damn thing after, before, or simultaneous with another. It is the most perfect description of actor-based threading you'll ever find. Actor computation is really dull. Actor-based concurrency is just one damn message after another. It really is a world of sequences. That's all it is. Now, if we want to understand this as an object model, it's worth understanding how other people approach things like organizing objects with respect to concurrency. One of the classic ideas is the monitor object concept. This is kind of like a Tony Hoare approach, the idea that an object, each method is effectively its own zone of mutual exclusion. It has its own critical region. This informed the design of both Java and C#. And we may say, okay, let's just deal with a phone book example. Simple phone book concept. You can update an entry, and that's an upsert. It'll update an entry if it's already there. It'll insert it if it isn't. We'll update a name with a number. We can drop any key, and like likewise, that does nothing if there's nothing there. And we can also find things. The result of that is optional. If it's not found, optional is not set. If it is found, then it is set. And we're going to throw threads at this, so we need to make sure that that is lockable. One of the actual use for mutable, in the sense that we want that to logically look like a query, but on the under the hood, there is change. Okay, so there's a whole bunch of stuff here. There's code and stuff. Fine, that's the basic logic. What does that look like in practice? Well, in practice, what we can do is we can set up a phone book, set up a directory. We can go and try and find something. The result of that will be unfound. Thomas Anderson is not in there because the directory is empty, it's fresh. That's a separate thread of execution over here from the thread of creation. Now we're going to have another thread that's going to update it. Thomas Anderson, they are number 1. And we now look for Thomas Anderson, and they are found. So in the separate thread, so if we do this by timeline, then they become found. And basically we would refer to this kind of sequencing. We can't find Neo. Let's update with Trinity. She's there. Morpheus is there. Thomas Anderson, we're going to drop him. He's no good. Update Neo. He is the one. And we just kind of go through and so on. So what we've got here is although we refer to it as monitor objects, what we're dealing with here is a particular kind of sequential object. There are 2 kinds of sequential object. Those that can only be used correctly in a sequential environment. In other words, they don't show them any other threads. They won't respond well. Okay, and there are those that are like truly sequential objects. They are passive, but they are also able to be safe in a threaded environment, and that will involve some degree of locking or a low lock approach. But the idea there is that the object itself is passive. It has no thread of activity itself. Now, if you want a thread of activity, then you switch to a different style, active objects. I'm not going to explore all of the code for this for reasons of time. Very similar to what we had before, except for one little thing. There is a function call operator there. I could have chosen anything. I could have called it run, but I'm going to make the personality of this like a function call. We've got the update. Drop looks identical, but the find looks a little bit different. When you find, this is one of those cases, it's all dots and angle brackets. This is in competition to try and make people feel good about using XML. So what we have here is a find does not optionally return a string. It returns a future to an option, which if you're in the derivatives business, it's like, what? Hang on. So we've got this idea. What we're saying is, this is all about maybes and possibilities. So I want to find something. Yeah, maybe you do. That's great. Well, what are you going to give me? Oh, I'm going to give you an IOU. What's the IOU on? A maybe. Maybe it is, maybe it isn't. Are you feeling lucky? But nonetheless, there is that idea. Now, if we rummage around in the private section, we see that there's activity. It's got its own thread. Okay, it's got a soul, if you like, and the idea is if it has a thread of activity, it is actively doing something, and it holds an internal queue of effectively function objects. And each one of these doesn't actually do anything. What it does is it creates a lambda and pops it in the queue, and whatever is launched by this function sits there just peeling things off the queue one at a time. I was called with this. I was called with this, and these are asynchronous, these ones, and this one is where we get a result back. Okay, so we will set the result and somebody will come along later and pick it up. So the active object the monitor object in this case is actually the win for a phone book, unless there's other housekeeping activities going on, because you can be doing other things. That's the sort of the joy of this. So the only difference here to recreate the previous sample, then you've got the phone book directory, you have to launch the directory, you have to run the directory. That's the only extra thing here. And in terms of usage, if we want to make it perfectly synchronous, in other words, kill all the benefits that we might have otherwise achieved, then we just get the find, do the get, and so on. Okay, so all of this leads to these two models. Active objects are not the same as actors. It's the reason I've included it here, because sometimes people confuse the two. It's very natural, because They both have threads. They both begin with the word act. And sometimes people throw the word object in to talk about act or object. So there's a sort of a sense they might mean the same thing. And that's not quite the case. So if we look through what we mean by an actor, I'm going to go to that old standby, a bunch of books. A bunch of books about objects. These are actually psychological objects, psychiatry to be precise. Freudian worldview, you see the self and the object world, they talk about the same things as well. This is a book on debugging, the shadow of the object, and so on. So what I really want to talk about here is this is a stack. So we need to learn about stacks. And stacks have, from the point of view, borrowing some of the vocabulary from CSP and kind of twisting the notation a little bit, the language of a stack, it's alphabet. Okay, it's alphabet. What can a stack talk about? Well, it can talk about push, pop, popped, and empty. Okay, I'll clarify what those are later. But you can push something onto it, you can pop something off it, but it doesn't happen synchronously. These are inbound messages, these are return messages. If the stack is empty, when you pop it, you get an empty message back. If you pop something and there is something, you get a separate callback saying, hey, here's the thing I popped. Okay, so we're going to split this so there's effectively no result. And then, here are all the possible conversations you can have using such an alphabet. You can create a stack and do nothing with it. You can create a stack and push something on it and then do nothing with it. You can create a stack, pop something, and get an empty response, but you can't pop something and not get a response. You can push, and then be done with it. It turns out there's an infinite number of these. That ... is curiously deceptive. But, you know, if you've got an intern in the office, you can have them generate this. No, we've got a better way of describing this. It's a simple state model allows us to do this. So what we've got is the idea of an empty state and a non-empty state. You push, you become non-empty. You pop, and if you've just got one item, you go back to this, sending out a popped message. If you pop from an empty state, you send out an empty message. If you push in the non-empty state, you remain non-empty. If you pop and you've got more than one element, you remain non-empty, but you send back a popped thing. Now, if we do this in Erlang, which is a language rather well suited to this approach, then I'll throw everything at you at once. This is a function definition. It is a function called empty. In other words, we're going to represent a state with a function. And this function does not change anything directly in the outside world. And Erlang is interesting because it has only two conditional constructs, if and receive. These are its language primitives. There is no loop. If you want a loop, you call yourself recursion, tail recursion. That's how we get around the infinity problem, tail call optimization. Okay? You just call yourself, you do it again. The easiest way to read any form of tail recursion in such environments is become, in other words, or remain empty. Okay? So receive, we can get, this is a tuple in curly brackets. Push, anything in lowercase is a symbol. So I want to push, here's a variable, it's got an uppercase. Push, here's the new top. We become non-empty with the top. And then if somebody says, I want to pop, then this is the return address, somebody you send it back to. We return the status of empty and continue being empty in both cases. Okay. Now it gets more interesting. Non-empty, we receive. If we get a push with a new top, we become even more non-empty with a new value. If we get a return, then we drop our value and become whatever it is, whoever it is that called us. So there's an interesting thing here. This is actually the call stack. You are actually interacting with a runtime stack. Effectively, the stack is the runtime stack. Now notice that all the synchronization that we're looking at is implicit, is availability. In other words, we have defined availability in data flow as our model of synchronization. So visibly, we're not thinking synchronizing, we're thinking what's the next value available. Okay? And if we run through it, launch a new stack, I'm going to send it a message, pop, and send it back to me, self. It's empty. I'm going to push 42, we get nothing back. Then I'm going to say pop, we get back pop 42. So now we're talking to an empty stack again. Now, push 20, push 17, pop self, get pop 17. That was the last thing pushed. So there's a stack there, if you like, of empty, non-empty 20, non-empty 17. When I talk to that, it returns popped 17, and we're now, the call stack is only 2 deep. It's got a non-empty 20 and an empty. And then we can move back down to that. That's kind of cute. What does the phone book look like? Looks like this. Any variant type, universal variant type, it's a function, phone book. Entry, I'm going to have an entry. It's got a name and a number. I'm going to have no entry. It's got a name. I'm going to have find, name, and whoever called me. I'm going to use a queue because I'm not going to create a full actor model in the slide. We don't have enough time. Here, if you've got a result, send it back to this guy. Okay? Great. What's the phone book look like? Well, it's a function, but it's masquerading as an object. There's our entries. That's our private state. It's so private that you can't, that it's actually inside a function. That's how private it is. And then we're going to repeatedly pick up requests, and we're going to interpret them. And we read off from the queue that we've been given that identifies us. That's our receiving queue. And then we do a whole load of type laundering, which is a bit of a pain in the backside. But, you know, oh, if that's an update, then assume it's, yeah, okay, right. So that's a little bit messy. This is left as an exercise for the reader. This is homework. You can turn it into something a little tidier by doing a little bit of overloading. It's very rare I ever load the double pipe operator, but it seemed to be one of the better ones for this one. You take the request and you launder it through multiple lambdas. Here is how you deal with updates. If you get an entry, it's an update. Here is how you deal with no entries. We'll treat that as equivalent to drop. And here's how we deal with find queries. Those are lookups. And so that works quite nicely and starts looking a little bit more like actor-based languages. However, that's your homework, should you wish to accept it. And the interaction, obviously it's a little bit longer because I haven't tidied up, I haven't given you a sort of tidied version. But what we're going to do is we're going to say that's our directory. We're going to identify it by a queue. And we're going to launch an actor. We're going to thread it and just fire and forget. And this is me here. What I'm going to do is I'm going to say, right, so all of my interactions are now message sends. Here's a data structure. Thomas Anderson, this is where I want the result. Please send it back to me. I've sent a request off. I'll get a result ready. Receive it, and that should be no entry at this point. Different thread, I'll send an entry, Thomas Anderson, his number is 1. Then we send Thomas Anderson, send us a result back, and that should be found, and we get that back, and so on. So the model looks a little more like message sending. If you want to fake it up with other things, you can sort of add syntax sugar to taste. But there's a very simple idea here, which is quite different to the way that people would approach active objects or indeed monitor objects. And what is interesting here is that what we've done is we are not talking about people locking things. The whole goal here is to decouple things. Immutability, I gave a talk on that a couple of years ago, but this is the other side of it. It is the idea that you can get an awful lot of stuff done by recomposing and reorganizing the model. And it's quite compositional. It scales rather nicely because it's not based on waiting for people as its fundamental construct like synchronization. Okay, so on that note, I'll give John Carmack the anti-penultimate word. Programming in a functional style makes the state presented to your code explicit, which makes it much easier to reason about. And in a completely pure system makes thread race conditions impossible. We might not be able to achieve the impossible, but the basic goal is exactly this. Think outside of that synchronization quadrant. It confines you. To think in terms of concurrency is not necessarily to think in terms of raw threads, and therefore not necessarily to think in terms of locks. And whenever you are thinking about putting a lock in, please remember this. Thank you very much.